All right, our next topic is an application of joint probabilities called Buffon's needle. So this is a very interesting application. Buffon's needle. Okay, so here's the problem. So we have a needle. This is a classic problem in probability. We have a needle, and we're going to uh, throw the needle up in the air and rotate it. Okay. Okay, it's going to rotate. And so we have a rotating needle. Of length L, and the length of the needle is less than D. And D is so this is being tossed on a grid of parallel lines spaced distance D apart. Okay, so we've got a needle. This is our needle. And this is our grid. And so we imagine throwing the needle in the air, rotating it 360 degrees. So it's going to be rotating, and it's eventually going to land on the ground. And let me just distance D, etc. And so these are all D apart. It's going to land on the grid. Well, L needs to be smaller than D, so let me make this a little smaller. Okay, and it's going to land on the grid, and the question is, does it land? Let me remove this just for simplicity. The question is, does it land intersecting one of the grid lines? Okay, so what is the probability that the needle comes to rest intersecting one of the grid lines? Okay, so in this example, it did come to rest. Now, what's affecting this? Well, one thing that's affecting is the fact that the needle is less, even if we put the needle perfectly perpendicular to the grid lines, there's a chance it would fall in between because L is less than D. Okay, but there's the possibility that a needle lands vertical, and in that case, doesn't really matter where it falls. The chance of it falling exactly on a grid line is very small, is pretty much zero. So not only does the location of where the needle falls, but also the angle affects whether it's going to intersect the grid line. So this is we're going to jointly model two aspects of this to get the answer. So we're going to define two random variables. X is going to be the distance from the center of the needle . to the nearest grid line. And A is going to be the angle with respect to the perpendicular. That we drop to the nearest grid line. So in this example, X, so here's the center. Made this really small, which makes it hard. Here's the center. Here's X. And the angle here is A. Okay. So how are we going to model this? Well, we're assuming that we're rotating the needle in a kind of a chaotic fashion, right? So that means that X is going to come to rest. So the distance, so we're throwing it on this grid and it's going to come to rest. And the nearest grid line is at most d over 2 away, right? Because if we split this in half, if the center of the needle's on the other side, the left side is going to be closer to the other grid line. And so we assume that it's thrown in a way where the needle falls is going to be uniform in that region. So X is uniform. And it's going to be uniform between 0 and d over 2. And the angle is similarly, it's going to be anywhere from the nearest, so it's always going to be something between minus pi over 2 and pi over 2. Right, so if in this case, this is something that's, let's just think about the possibilities. A vertical is pi over 2 essentially, or negative pi over 2. So it's not clear. So we'll only include one of the endpoints. If it's a little bit over, then we have an angle like this. And if it's like this, pointing this way, right, then we have a negative gradient, right? So the angle is uniform. And we will say it's uniform minus pi over 2, pi over 2. We're going to ignore the possibility that it's perfectly vertical because it's so unlikely and it doesn't affect anything because it's a single point in a continuous distribution. And furthermore, we're going to assume that X is independent of A because we wouldn't expect that where it falls is going to affect how far it falls affects the angle because we're assuming that it's being tossed in a chaotic fashion. Okay, so given this information, okay, what is the density? Well, Fx, right, of X is 2 over D times the indicator that X is between 0 and D over 2. Fa of A is 1 over pi indicator that the angle is between minus pi over 2 and pi over 2. So this tells us then that the joint density of X and A is just a product by independence. So this is equal to 2 over pi d times these indicators. The indicators are extremely important, by the way, because they're going to keep you out of trouble. So you don't have to write them in. You can technically just say these are the bounds that X and A have to fall between. but you get yourself into trouble that way. Um, what I mean by that is when you change variables or when you calculate integrals over certain regions, you might lose track of what the bounds and what the limits of the variable are, and you end up integrating over a bigger or a smaller region than you're supposed to, or just the wrong region altogether. So be mindful of that. Now, what's the event that we're interested in? Well, for the needle to intersect a grid line, what do we need to happen? Okay, let's think about this. We want to define a region B, right? We want to define a region B. Well, what's going on here? So we have grid lines. I'm gonna write it a little bigger here so it's easier to see. We have the needle. I don't want the center of the needle to be so. Okay, let's make this. Okay, good. So now we have the needle. Now, what we know is, okay, this here has an X. This is X, right? And this is A. That would have a grid line. That would intersect, right? How do we know based on X and A? So given X and A, how do we know if the needle intersects? Well, let's look at an alternative. I'll do another one here, which is, what's an example of one that doesn't intersect? This one, right? So in this case, well, yeah, this one didn't intersect. So what's going on here? Well, X is too far away, given the angle, okay? So what can we say? Well, realize that if we know X and A, we know that the length of this needle is L. So we know that this piece is L over 2. And we drop the perpendicular, so we can use a little trigonometry here. And we know that the horizontal, the adjacent side is L over 2 cos A. And the other side is L over 2 sine A. We don't need that. And so what we can see then is that if we consider that in this case, and we consider it in this case, we have the case where X is either less than L over 2 cosine A or bigger than L over 2 cosine A. So we define B to be the set of X's and A's such that X is less than or equal to L over 2 cosine of A. So in order to calculate this probability, the probability that we're interested in is probability that needle intersects a grid point. This is probability that X A is in B, but we've just defined this as probability that X is less than or equal to L over 2 cosine of A. Okay, how do we do this? Well, we have a joint distribution, so possible values of X are anything from 0 to D over 2. Hold on. A is unrestricted here, so possible values of A are anything from minus pi over 2 to pi over 2. And then given A, X can be anything from 0 to L over 2 cosine A.
And the joint density we already know is 2 over pi d on that region. We've already taken the limits into account. Dx dA. So now we can just do the integral. Okay, so if we do the integral, what we'll find is 2 over pi d is a constant, right? So 2 over pi d is a constant. Pull it out. Integral of a constant is just 1. Well, it's just x, and then so we just get the limits of integration. So this ends up being minus pi over 2, pi over 2 of L over 2 cosine of A dA. Integral of cosine is sine. So we get 2 over pi d, L over 2. So we get L over pi d sine A from pi over 2 to minus pi over 2. Okay. What's the sine of pi over 2? It's 1. What's the sine of minus pi over 2? It's minus 1. So it's 1 minus negative 1. So that's 2. And so the probability is 2L over pi d. So that's a pretty, I believe, a pretty interesting application of, even though we have independent random variables, it gives us a very powerful way to, very interesting way to calculate this probability, and we can do it and we get a closed form, right? So it's very interesting. So what we see is that even if L is the size of D, right, the width of D, there is still, of course, a probability that that we don't get intersection, right? Because we of the angle. And so in that case, if L is equal to D, we get probably 2 over pi. So something very very interesting application of joint distributions here. This was called the Buffon's needle.